Question 5. Figure 11 shows the stress-strain graph for a metal in tension up to the point at which it fractures. Linear section, this is where extension becomes fractured here. This is strain times 10 to the power minus 4, and that is stress times 10 to the power 6. M mega is 10 to the power 6. And question 5.1, determine using figure 11 the Young modulus of the metal. So we find the linear point. We can pick any one of those. So I'm picking that there. That's still linear. So if this is 5 and that's 10, this must be 7.5. Each little box, 2 boxes 1. And for this one, this is 0 to 50, and that's 50 to 100. Each little square here is 5. So that would be 105. The gradient would be the height over that length. We can write E for the Young modulus equal to stress over strain. That's equal to gradient, and the stress is 105 times 10 to the power 6 divided by strain 7.5 times 10 to the power minus 4. You can rewrite it as 105 divided by 7.5 times 10 to the power 10. Indices, the 1 over 10 to the power minus 4 will become 10 to the power 4, and 10 to the power 6 times 10 to the power 4 is 10 to the power 10. 105 divided by 7.5 is 14, as 1.4 times 10 to the power 11. 1.4 times 10 to the power 11 Pascal. Question 5.2, explain how the graph shows that this metal is brittle. We can see that the wire undergoes only a very small increase in strain beyond the linear section before fractured. It's only a very small increase in strain before it fractured. Figure 12 shows a uniform rigid lighting beam AB suspended from a fixed horizontal support by 2 identical vertical steel wires. A lamp is attached to the midpoint of AB. Here's figure 12. The unloaded length of each steel wire was 1.2 meters before it was attached to AB. Length is 1.2 meters. AB is horizontal. We got the mass of AB to be 4.4 kilogram. The mass of lamp is 16 kilogram. Distance between wires is 2 meters. Diameter of each wire is 0.8 millimeter. Young modulus of steel is 2.1 times 10 to the power 11 Pascal, 5.3. Calculate the extension of each wire. So we know that force is equal to weight in this case, which is mg. Area is pi r squared, which can be written as pi d squared over 4. The total force or load will be equal to the mass of AB plus the mass of lamp times the gravitational field strength, and that will be 20.124 newtons. E, the Young modulus, is equal to stress over strain, and stress is force over area, and strain is extension over length. And that can be written as force times length over area times extension. We're trying to find extension of the wire, so we can make E the subject, and E will be force times length over area times Young modulus. So what we need to do now is populate it with the values and replace the d, because area is pi d squared over 4. So that will be the area. Because there are 2 of them, so there's that and that, so my area will be times 2 for the steel wire, and then times it by the Young modulus here. 2 cancel that 2 there, so you get 2 at the bottom, and that 2 then goes up here, because you get 1 over 1 over 2. 1 over 1 over 2 is 2, so that's why that 2 goes up there. And you got the pi times the diameter squared times Young modulus. And if you compute that on your calculator, you get 1.14 times 10 to the power minus 3 meters. Question 5.4. The right hand steel wire is removed and replaced with an aluminum wire of diameter 1.6 millimeter. The unloaded length of the aluminum wire is the same as that of the original steel wire. When the lamp is at the midpoint of AB, one of the wires extends more than the other so that AB is not horizontal. To make AB horizontal, the lamp has to be moved to a distance x from A. Figure 13 shows the new arrangement. The Young modulus of aluminium is 7 times 10 to the power 10 Pascal. Deduce distance x. We need to find that distance. Okay, so what do we have? We have the EA for aluminium and E for steel. E for aluminium is 7 times 10 to the power 10, and E for steel is 2.1 times 10 to the power 11. And you can see E for steel here, which is 2.1 times 10 to the power 11. And the ratios of those two, if I write them up, that is actually 1:3. Right, so this is the tension or the force in the steel wire pulling the weight up, and likewise the force on the aluminium wire pulling that weight up. And we also have the weight of the beam AB mg, and that would be 4.4 g. We have the weight of the lamp, which is 16 g, not grams. G is gravitational field strength. We also have this information, the mass of AB, which we got there, the length of the wire, which is 1.2 meter, so this length is 1.2 meter. The mass is 16 kilogram, and that's 16 kilogram there. And the diameter of the steel is that, and this is the diameter of aluminium. That's the Young modulus of steel, and that's the Young modulus of aluminium. Write down the equation for Young's modulus, and that we note from this equation that the length is the same for both the steel and aluminium. Extension is constant, and pi also constant. Why pi? Because pi is in the area here. So if I write the area, pi d squared over 4. Now I can see, because E and pi and L are constant, so we can ignore those because 4 is constant, so we can ignore 4. So we can say E is directly proportional to F over D squared, because F and D will be changing. So we can then say F is proportional to E D squared. We got a relationship there now. Why don't we take moment about A? This is A here. We're going to take moment here. And if we do that, we get 16g times x. This is 16g times x, and that times that, plus 4.4g times 1. So this beam here is in the middle, and that diameter is 2. So that will be 4.4g times 1 to A. And that must equal to the FA, that force here, times 2, because that distance is 2. So that will be times 2. So that's the first moment we've taken about A. So why don't we balance the forces as well? That force and that force must equal to those forces acting down. Vertical forces, so we can balance the vertical forces. FA plus FS, because they're pointing up, will be equal to the 16g, that's gravitational field strength, plus 4.4g. So that'll be balancing the vertical forces. And we can bring in this ratio here. So we have FA equals to EA dA squared. FS, that's for steel, equal to ES ds squared. So we can divide one over the other. So FA over FS will be equal to EA times dA squared over ES times ds, because they are ratio, one for steel and one for aluminium. So we're going to use all these to find x. So now we know the ratio now, because EA over ES times dA over ds all squared. So I've taken this squared out, and we can then write the FA, which is what we're looking for, will be the EA times FS, so making FA the subject, over ES times dA over ds all squared. We know what dA over ds is from the data we're given. You can see dA and ds. The dA over ds will be a ratio of 2, because this is half of that. So that'll be 2. You see that's dA and ds. Why don't we plug those values here? We know EA over ES is 1 over 3. And dA over ds is 2. So if we plug those in, Fs times 1 over 3 times 2 squared, that will be equal to 4 Fs over 3 equals to Fa. So that is the relationship that we have. We've got this relationship now. Now we can use this and that to find x. We can use this or we can use that. So let's use that as well. So this will be FA plus FS equal to 16 plus 4.4 or G. So that would be 20.4 G. So that is 20.4 G. You can then simplify, multiply everything by 3. So we get 4FS plus 3FS equals to 61.2 G. Now I can find FS. 7FS equals to 61.2 times 9.81 because G is 9.81 and FS is 85.77 newtons. FA will be 114.36 newtons because I've just taken that value and put it here to then find FA. Now I know FS and FA values. I can then use that here to find X, especially the FA value. So making X the subject here, I take that to the other side, divided by 16G. So 2FA minus 4.4G divided by 16G. And plugging the values in, I get that. So that's FA value. 2 times FA value minus 4.4 times 9.81 divided by 16 times 9.81. Then X is 1.18 meters. So I can write the X value to be 1.18 meters.